Okay, so this is basically the first kind of multi-period model that we're dealing with. And the idea is that what happens in one period affects the next period. So we have three different periods, autumn, winter, and spring. And in each of these periods, we have a production cost. Energy prices are higher, I guess, in winter, so it costs more to produce in winter. We also have an inventory cost if we hold our inventory on um, to the next period. So let's just start off with all zeros. And the idea here, the model is to the right. And again, this is on page 502 in the textbook that explains it a little bit more, is our optimization function. We're basically minimizing our production cost and our inventory holding cost. So we're minimizing both of those. And the idea is we have kind of an equation constraint equation at each stage. So in the first stage, we need to basically ship out 150 units. So we produce a certain amount, we hold some in inventory, and the leftover is this demand, this 150 units. The next period is exactly the same, but we also have the inventory from the previous period. And then this goes on to the next period. So we can actually write these three equations into Excel. So our kind of how much demand we send out is going to be the production minus the inventory. So the idea here, if we have a demand of 150, we produce 500, we've got to hold 350 of that in inventory for this equation to match the demand. You see here, so say I type in 300 and 200, then I don't match the demand of 150, but 300, 150 works perfectly. Now, in the next period, it's going to be the same. So this is going to be, we're going to set the demand eventually to be equal to production minus inventory, but we also have the inventory we've held over from the previous period. And again, we're going to do exactly the same thing in the spring. So it's going to be production minus inventory, but plus the inventory from the previous period. And again, this is going to be equal to the net production. So here, for example, we had 150 over from the winter. If we produce another 250 and don't hold anything over, we've met the 400 demand. And then in the spring, we only have demand of 50. Then we've actually matched the equations here. So that was just a way of matching the equations. Now the costs are quite nice, the objective function, because it's production times the unit production cost and inventory times the inventory holding cost. And we can actually do this just this in a giant sum product. And that would give us the cost. So say, for example, again, if we have the 300, 150, then you see we've been charged $11 per unit for the production. And we're holding over 150 inventory. And we've got an extra 150 times 110. Sorry, $1.20. Okay, so let's just run this using Solver. So our objective, I think I pressed the wrong button there, is this, and we want to minimize the cost by changing these cells here. Okay, so we have the minimizing here of this variable by changing these 6 variables here. And then we need to add our constraints. We already know these values are greater or equal to 0. So we have this selected. We're going to add. And basically, it's just the demand constraints. So what we have over between production and inventory is our actual demand that we've taken away. And there we have demand constraints. And all we really have to do now is it's a linear program, so we might as well use the dedicated solver. So let's select these. And we can see here, so this is the result. We've got basically 550 in the autumn. So we've produced a lot in the autumn as it's cheap to produce here. And we've held over the 400 for the winter. But in the winter, notice we've not produced anything. We've not produced anything excess because we might as well wait until the spring when it's cheaper to produce the remaining 50 for the spring. It doesn't make sense to kind of hold it over further. And we could have produced the spring in the autumn as well, but then we'd have paid 2 different inventory holding costs, and $11 plus $2.40 is greater than the $12.50 to produce in the spring. So that's kind of relatively intuitive, and our optimal is 7,155. And let's look at our reports. The answer report is pretty obvious. We have the total cost. Notice these are equality constraints, so they have to hold. They have to be bounded. We have to be on the boundary of the solution. So all these 3 constraints are bound because we produce 100. We kind of have demand of 150, demand of 400, and demand of 50. And our variables we produce in autumn and spring, and we hold over the inventory in the autumn. Sensitivity analysis. Now remember, the reduced cost is, the change in the objective to get our variable in the model. So to produce in the winter, our production cost for winter needs to be 1.8 less. And that just means if the production cost is 1.8 less, it's now less expensive to produce in the winter than to produce in the autumn and pay the inventory to hold over. And again, it's the same, for the inventory for the winter and the inventory for the spring. Not quite sure what happened with the inventory for the spring, but we'd have to reduce it by a lot in order to make. I get this. It's because inventory for the spring, it doesn't actually make any sense. We'd need a negative value for it to be worthwhile because we'd be holding the inventory over to the next period, but it's the last period, so there's no demand. That's why we get this weird, really high value. And the shadow prices, again, this is just, if we increase our demand in autumn, we've got to produce, every increase in demand, we've got to produce more items, and it costs money to produce the items. You see, this is the actual production cost. This is kind of the production cost for the autumn plus the 1.2 to hold over. So this is how much extra it would cost the objective function to produce 1 extra in each of these 3 periods.